This absolute gizmo, which looks like something that Bruce Willis would have to disarm in a 90s action movie, actually plugs into any standard electrical outlet and makes pure oxygen out of thin air. Today, I'm going to tell you how I built this for about $1,300, a little bit about the open source project that it's based on, and of course, the science behind how it works. Welcome back to Signal Ditch. I'm Nick, and this is a propane flame. Now, this is reasonably hot. It is fire after all. I wouldn't leave my hand in there for very long, but notice how yellow and sooty this flame is. It's not getting as much oxygen as it wants from the air around it. And if I want a flame that's capable of, say, melting a piece of borosilicate glass, I need to feed it more oxygen. A blue flame like this, which doesn't produce soot and has a visible bright blue cone at its base, is much, much hotter because I'm actually burning all of the propane in the fuel stream by adding enough oxygen to fully oxidize it. In order to work the hard borosilicate glass that I need for my vacuum tubes, I need a flame like this. The only problem is, a flame like this takes a fair amount of oxygen to sustain. And most of the time that means a big old oxygen tank that you need to rent from a welding supply, occasionally put back in your car, take back to the welding supply, and pay to have refilled periodically. All of that is boring and bad and sucks. So why can't I just take the oxygen out of the air that I'm already breathing? I mean, there's tons of oxygen all around us. It's just, you know, puffed up with all this extra nitrogen and junk. It turns out there's a way to do that. It's called a pressure swing adsorption oxygen concentrator. And glass blowers have been using these for a long time.
The rest of that segment was basically unusable. So, welcome to voiceover land, where I'm going to explain how pressure swing adsorption works. Let's start out by taking a look at air. Just normal atmospheric air. You know it, you love it, you breathe it every day. Probably about 78% of this is nitrogen, which I've depicted here as 2 circles because that's going to come in the flavor of a diatomic molecule called dinitrogen. And actually the same is true of oxygen, which makes up 21% of the air that we breathe. And then there's about 1% of other stuff in there, and it turns out that most of that other stuff is argon. So if you want to take this mixture of gases and you want to distill it down to something that's mostly oxygen, your best bet is going to be just to filter out all of the nitrogen, right? We get rid of the nitrogen. Even if we have trace gases left over, this is overwhelmingly oxygen. So I think that's going to work out pretty well for us, but how do you actually do that? Well, it turns out the answer to that question is fancy sand. By fancy sand, of course, I mean zeolites. Zeolites are a mineral. They're a crystalline aluminosilicate. They do occur in nature, but today we're talking about these sort of synthetic zeolites. Now, because these are crystals, they have a very regular structure, and because they have this regular structure, they have a very uniform pore size. And these pores are what allow it to act as what's called a molecular sieve, which sort of selectively traps molecules inside of those pores based on the size of the molecule. Let's say that these hexagons represent our zeolite molecular sieves, and we reintroduce our atmospheric air from earlier. Now, some of these molecules are going to adsorb onto the surface of the zeolite, and we can actually make more of them adsorb onto the surface just by increasing the pressure in this container, right? So as we increase the pressure, there are going to be more molecules packed into this space. They're going to be moving around and bumping into each other and causing collisions that sort of wedge them deeper into this pore structure of the zeolite. And the nitrogen is going to get stuck in the zeolite much more easily than the oxygen is going to, and that just has to do with the size of the pores in the zeolite compared to the size of the dinitrogen molecule. So if we bleed the pressure off of this container, we'll see that a lot of these molecules actually didn't get stuck, and they'll just sort of leave all of the nitrogen stuck in the molecular sieve bed. Then, if we want to unstick those nitrogens, we could just lower the pressure again, They'll sort of pop back out of the pores in the zeolite, and then we can blow those out, and we have a fresh bed of molecular sieves ready to process more atmospheric air. And if we go and look at all the stuff that we blew out of the sieve bed earlier, that's mostly oxygen, right? We've got our oxygen, we've got maybe a few stray nitrogen molecules, and then a lot of our trace gases are going to blow right through there. So yeah, I mean, this is great. This is what we're looking for. This is going to be great for running our torch, but how do we do this sort of practically speaking? This is a diagram of a pretty typical pressure swing adsorption system. We've got our two sieve beds here, we've got 3 valves, and then 2 restrictions at the top of the system that limit gas flow through to the outlet. The PSA cycle is a little easier to understand if we go ahead and just cover up half of the system and focus on one of the molecular sieve beds. At the beginning of the cycle, we open the first sieve bed to the air compressor and fill it with compressed air. The orifice at the outlet of the sieve bed allows pressure to build inside, increasing the adsorption potential of the zeolite, and so all of the gas that's coming through the orifice and exiting the system is going to be highly enriched in oxygen. If we continued to run the system this way, eventually the zeolites would become saturated with nitrogen, and we'd start passing just normal air out of the outlet of the sieve bed. So we actually need to stop the flow of compressed air into the sieve bed for a moment so that we can flush all of the nitrogen out through the exhaust port. This is achieved by switching the valve at the bottom of the sieve bed from the compressed air source to the exhaust, and then opening a valve that allows oxygen from the other sieve bed to flow backwards through this sieve bed, purging the nitrogen. After the purge cycle, we close both of those valves, cutting off the sieve bed from atmosphere entirely, and it just sort of sits here, filled with mostly oxygen. Once the other sieve bed has completed its portion of the cycle, we actually open these valves again and use the incoming compressed air to push some of this oxygen across to the other sieve bed, which is actually its purge cycle. And now that we've seen this cycle happen in one sieve bed, we can watch it happen in both of the sieve beds simultaneously, and you'll start to understand why this is called a pressure swing adsorption system. Notice the path of the orange arrow, which shows where most of the flow is happening in the system. So we pressurize one sieve bed, we'll call that bed A, and we get a stream of pure oxygen out of the system. Then we close some valves, open some other valves, and we reroute the flow of compressed air to the other sieve bed. We'll call that bed B. The flow actually goes from the compressed air through bed B, pushing oxygen that's left from the last cycle over into the top of bed A, forcing all of the nitrogen out of the exhaust. Once we close the equalization valve, bed B can actually start to pressurize, increasing the adsorption potential of the zeolite, and again purifying air into oxygen. After a few seconds, bed B becomes saturated, we open the equalization valve, and then we purge that using the oxygen left over in bed A. And that cycle continues, swinging back and forth between the two sieve beds. Here's some good photos of the front and back of my system as it's built, and some arrows showing what physical part correlates to what part on the diagram. You can see the valves are just little cheap pneumatic valves from Amazon. The restrictions or orifices are actually hidden inside of the hoses that go to that Y connector at the top. And then the sieve beds are these large 3-inch PVC cylinders. You might also notice that there's an extra cylinder hanging off of the side of the contraption. Now, I only described 2 sieve beds, so what is that? Well, now that you know how a PSA system works, you can imagine that the output comes in these sort of periodic batches, where the pressure of the output goes up and then comes back down and then goes up suddenly and then bleeds back down. And this happens, once every couple of seconds. So if you're trying to run a torch or something off of this output, your gas mix is going to be changing constantly. It's just going to be impossible. So how do we fix that? Well, we add a buffer tank. Now, the buffer tank is just a big empty tank with a regulator after it. And as long as that regulator isn't wide open, the pressure in the buffer tank can oscillate all at once, and the pressure of the regulated gas stream after the buffer tank will stay pretty constant. One question you might have is, what happens if you don't need the entire capacity of the system? In other words, if you don't want to run this thing wide open and you have this regulator on the output, what happens when you close down the regulator? Doesn't pressure build inside the system and damage something? Well, no, as it turns out, no part of the system is completely closed to atmosphere during any time in the cycle. So let's look at the worst case scenario where the outlet is just completely blocked. What you notice is that while the equalization valve is open, the compressed air can go into one of the sieve beds and out of the other sieve bed. But even when that valve is closed, there's still a path through the orifices from one sieve bed to the other and then to the exhaust. So you end up with this cycle where these two mostly saturated sieve beds are just passing atmospheric air back and forth until you open the outlet again, and then they can purge properly and start to make oxygen. In fact, as you begin to restrict the output, you might even start to see larger concentrations of oxygen as you are saturating less of the zeolite and your purge cycles become more efficient. Even if something went terribly wrong and there was a blockage in the system that allowed pressure to build inside of one of the sieve beds, my system actually has a 40 psi safety valve before the inlet to either of the sieve beds, so no pressure can build in the system beyond 40 psi. It probably makes sense at this point to talk about the project where most of this design came from, and that's a project called Oxikit. Oxikit is an open source design project that was started during the COVID pandemic to address an oxygen shortage in India's overcrowded and under-equipped hospitals. The idea was to design a portable oxygen concentrator with significant output capacity that could be built using components sourced locally inside of India, following instructions that almost anybody could understand using only very simple tools. I think the project achieves this goal quite well. The documentation is mostly in the form of build videos on YouTube that you can follow along with to build your own system. There are also a handful of supplementary written documents, things like a well-annotated bill of materials, a system diagram, and some troubleshooting tips. My oxygen concentrator is basically a one-to-one copy of the Oxikit demo unit. I only made a few modifications and substitutions where it was easier for me to get certain components than others. As an example, the Oxikit project uses modified PVC pipe fittings as the piston and the spring seat inside of the sieve beds. I think this is a genius move because it doesn't require you to have any advanced fabrication tools at hand to make your own components. But since I do have a 3D printer, I thought, why not design those custom components and then print them, and I can publish those for people who do have access to a 3D printer because it does actually make the build easier. In addition, I actually found it kind of difficult to source the spring that they specified for the sieve beds. It's a 2-inch diameter stainless steel peak-to-peak wave spring with a spring rate of 50 pounds per inch. Wave springs seem pretty fancy for this application, so I actually tracked down some traditional coil springs that had the same spring rate and the same diameter. They're not made out of stainless steel, but they are at least powder coated. They're actually transfer assist springs for microsprint racing suspension. They're a little longer than the wave springs that are called for in the documentation, but at $29 a piece, the price is right. And Hypercoil has them in stock, so you can just go and add them to your cart. You don't have to submit an inquiry to a spring manufacturer. The point of the spring is to keep the zeolite packed together tightly as you pressurize and depressurize the canister. Because gas moves both ways through the canister, you run the risk of shifting the zeolite back and forth on every cycle, which would cause it to rub together and eventually pulverize itself into dust. Not only is this dust an ineffective molecular sieve, but it can also get blown through the filter and into your output line. On top of that, the problem actually exacerbates itself. As the zeolite gets pulverized, it makes more room in the canister for the rest of the zeolite to shift back and forth. Having a spring-loaded piston inside the canister to hold the zeolite in place prevents or at least slows down this process significantly. Besides these minor adjustments, as well as some custom mounting hardware so that I could mount mine onto a hand truck, my machine is basically the same one you'll find in the Oxikit documentation. Here I am fabricating the sieve beds out of 3-inch Schedule 40 PVC pipe. It's recommended that you strongly agitate the canister as you're pouring the zeolite in. That way you make sure that it's all packed efficiently and it doesn't settle during the first few cycles and instantly take up all of the slack in your spring-loaded piston. In the Oxikit video, they use a pneumatic vibrator which they turn the air pressure down on so that they don't accidentally damage the PVC pipe in the process. I actually had success using like a Theragun style massage tool. I just cranked the settings on it and used the foam ball attachment so that I wouldn't create any hairline cracks in the PVC pipe. As you can see, it makes the zeolite dance around in the tube, and I haven't had any significant settlings since I started running the system. You definitely want to wear a good dust mask while you're doing this because there is a lot of dust in the zeolite from manufacturing and then from shipping, and the dust is going to be this aluminosilicate, mineral material. You definitely do not want that in your lungs. Speaking of which, where do you get the zeolite? Well, it turns out there are a lot of suppliers for this stuff because it's used in a lot of different applications in a wide range of industries. I bought mine on AliExpress. I paid about $55 a kilo for it, and it got to me within a few weeks. It even came vacuum packed in big metallized plastic envelopes.
Nice hiss.
I think I bought 4 kilograms just to be safe, but the project ended up using, I think, about 3 kilos. What you're looking for are 0.4 to 0.8 millimeter 13x molecular sieves. Usually the seller will throw in some keywords like PSA or oxygen generator so you know what you're looking for. Broadly speaking, there are 2 types of zeolites for this application. There's a lithium type and a sodium type. The lithium type are more efficient, but they're also more expensive. I ended up just using the sodium type, and so far it's been fine. If you're in a crisis situation where you're building this machine to use in a medical setting, or if you plan on breathing the output oxygen for any reason, then I would recommend being maybe a little bit more selective about where you buy your zeolites. You'll probably also need to add some other odds and ends like a water bubbler on the output to make sure that you're not breathing super dry air, and also to catch any zeolite dust that might make it through the system. As many lives as Oxikit has probably saved, I'd say that if you're in any position to avoid breathing oxygen made by one of these machines, you should probably avoid it.
Let me give you a tour of my system, starting at the bottom with this 2 horsepower oil-free air compressor motor. Now this is actually a replacement part for a California Air Tools air compressor, so it doesn't come with the accumulator tank, it doesn't come with any sort of sensor or safety valve, it's just the compressor and the motor as a unit. Now I bought this from Tractor Supply for under $300, I think, and that's pretty incredible for a 2 horsepower air compressor. And the output for this air compressor goes into a condenser coil. Unfortunately, because I do live in a humid environment, I need to worry a lot about how much water is going to be in the air before I introduce it to our molecular sieves. So I first put it into a condenser to help cool the air, and in the process condense a lot of the water out of it. This condenser is something that I bent by hand out of 25 feet of soft copper tubing, and it feeds into an overpressure safety valve. Now this should never pop during normal operation, but if something were to get clogged or if a valve just refused to open for whatever reason, this keeps the system from getting to a dangerous pressure. A lot of this is made out of, inexpensive pneumatic fittings as well as PVC pipe, so we don't want it to get to a high pressure. The nominal system pressure for something like this is around 30 psi. If you get higher than that, something is wrong. So a safety valve like this is just cheap insurance. After the safety valve, we go into a coalescing filter, and this helps remove most of the water from the airstream. Basically, this gives all of the water that condenses in the coil a place to drip out so that I can collect it here and remove it from the system. Unfortunately, this isn't going to remove all of the moisture from the system. And if you have a look at my desiccant dryer, which is directly after it, you can tell it's pretty cooked already. This desiccant has an indicator in it that turns pink when it's saturated, and this is some pretty pink desiccant. Fortunately, the desiccant can be regenerated. I just have to pop that in the microwave for 30 seconds, a minute or so. So I may need to get a larger desiccant dryer to put on the system. Now, of course, it doesn't help that I'm running this in a non-air conditioned workshop in the summer in the southeastern US, where the relative humidity is usually around, 70 or 80% or higher. This certainly is not the best environment for something like this, but it's where I am. So yeah, a larger desiccant dryer in the future, but for now, this is going to help. After the desiccant dryer, this hose takes the cool and hopefully relatively dry air to the bottom of the molecular sieve beds. Here's our hose coming from the other side, and it tees off into this valve and then elbows into this valve, basically splitting our compressed airflow into these two solenoid valves that control the flow of compressed air into the sieve beds. These valves are super cheap solenoid valves that I bought on Amazon for something like 15 bucks a piece. And they seem to do the job just fine. In fact, almost all of the pneumatic components, including these push-to-connect fittings and this hose, comes from the same supplier on Amazon, which, as far as I can tell, is just a cheap import supplier of little pneumatic gizmos and gadgets. The sieve beds themselves are made out of 3-inch Schedule 40 PVC pipe. Now, ideally, you wouldn't pressurize PVC pipe with air, but we're only talking about pressures of about 30 psi here, so I'm personally not too worried about it. You decide what's acceptable risk for you. At the top of each sieve canister is a dry pressure gauge. Now, it's important that you use a dry pressure gauge in oxygen applications and not an oil-filled gauge. An oil-filled gauge is nice for compressed air because it keeps the needle from waggling back and forth as the pressure fluctuates in the system. Unfortunately, if you're measuring pressure of relatively pure oxygen, in our case, maybe 92 to 98%, the oxygen can actually react with the oil in the gauge. And best case, it contaminates the oxygen, it turns the oil in the gauge to sludge. Worst case, it literally explodes. The two molecular sieve canisters are connected together through this two-way, two-position valve, which basically allows me to open up a passageway between the two sieves and equalize the pressure between them. Now, when this valve is closed, the two canisters are actually still connected, but they're connected through a very small pinhole orifice in both of these lines here, which tee together into the output line. The output line goes to the bottom of this piece of PVC pipe. Now, there's nothing inside of here. This is basically acting as a pressure vessel. This is our buffer tank. And this is the output regulator that comes out of the top of the buffer tank. This is a dry gauge air pressure regulator. Goes up to 150 psi. Of course, the output pressure on this system is never anywhere near that. And in reality, the pressure is not as important as the flow. So if anything, it'd be nice to have a flow meter up here. And in the future, I might add that. You can see the output side of the regulator actually has a flashback arrestor on it, as does the propane fitting that connects to the propane tank. This is both a flashback arrestor and a check valve, so it prevents a flame from making its way down the hose into either our buffer tank or, in the case of the fuel side, the propane tank. It also prevents gas from leaking from one of the tanks to the other ones, which could potentially produce an explosive mixture inside of a pressure vessel. So we want to do anything we can to avoid that. These are very cheap considering how much headache they can save you in the long run. The whole operation is powered and controlled from the modules on this DIN rail. This is a custom PCB that I made based around this Pro Micro C, which is just an Arduino development board. And the breakout board basically gives me the ability to control higher loads using the outputs on the microcontroller board. So I have a couple of MOSFETs here. I also have a couple of resistor dividers coming to the ADC on this so that I can read higher voltage sensors. Now, there aren't currently any sensors on this system, but in the future, I may want to add pressure sensors or flow sensors just as safety and convenience features. And so I thought I might as well build that in now. Next to it, we have a solid-state relay. This allows one of the outputs on the control board to actually turn the compressor on and off. This is a 5-volt DC power supply from Meanwell, and this is just powering our controller board. Next to it, we have a slightly larger 12-volt supply, and this is supplying the power both to our solenoid-actuated valves, as well as the cooling fan arrangement on the condenser coil. Now, this mini circuit breaker is not strictly necessary, but the compressor motor does represent a fairly large load, especially on startup. And if it were ever to stall or to get damaged in some way and try to pull a lot of current, it could damage other things on the rail. So I decided, why not? It was like $10, and I just put it on the rail. It goes between the mains input and the solid-state relay that controls the compressor. And finally, the mains voltage, which in my part of the world is about 115 volts AC, comes into this little terminal block, which distributes it, to our breaker, our solid-state relay, and our DC supplies. I added a few convenience features like this hour meter, which is connected to the mains terminal block and keeps track of how many hours the machine has been running. This will be really helpful in the future when the molecular sieves start to degrade and I need to change them. Hopefully it'll give me some idea of how many hours of useful life I get out of the molecular sieves. Once that baseline is established, this also works as a diagnostic device. If I find that the output is sagging after fewer hours than normal, I can go through the system and try to figure out why that's happening. Another quality of life feature are these 3D printed cord keepers that allow me to wrap up the mains cable when I'm not using the machine. And finally, I built the entire apparatus on this hand truck, or dolly, furniture mover. I'm not sure what they call this in other parts of the world, but surely you've seen one before. I already had one in my shop. I didn't go buy this for this project. In fact, I commandeered it for this project, and now I'll need to buy another one if I want to move heavy stuff again. That being said, I think this is a pretty reasonable solution. It acts a lot like the kind of cart that you would put a big tank of compressed oxygen on. Except if I knock this thing over, maybe I'll break it, but at least I won't knock a regulator off the top of the tank and have it shoot across the shop and go through a wall. All in all, I'm pretty happy with what I've built here. For $1,300, the output is totally satisfactory, and it's going to save me a lot of hassle in hauling around oxygen tanks. I think the capacity is going to be plenty for the next couple of years of glass blowing projects and, who knows, chemistry experiments, just anything where I might need some relatively pure oxygen. If you enjoy projects like this, consider supporting me on Patreon at patreon.com/integratedtherm. My patrons are really the only reason that I can afford to build something like this as a hobby. Now, it's been a while since I've put out a video, and part of that is things happening in my personal life, but part of that really is just because it's expensive to build something like this. So I'd put together a little shopping list for the next phase of the project, wait for the Patreon money to come in at the beginning of each month, and then I'd buy some parts and keep working on the project. Now, I could be better about updating the Patreon, and I intend to be. If you go there now, you'll find 2 blog posts about the building of this project, as well as a spreadsheet that breaks down every part in this, what it costs, and a link to where you can buy it. All of that is available on the free tier. If you can toss me a couple dollars a month, you can also get notified before videos go out and get some behind-the-scenes writing and pictures of projects that are in progress. Thanks for watching, and I'll see you next time.